Welcome to the basic training of LIPS products. The purpose of this training is to let distributors understand quickly how to explain to customers 1. The benefits of using 3D cameras with LIPS Edge products. 2. The distributor can grasp quickly concepts. 3. The distributor can understand to produce images and show to customers. This training will cover topics in the following order. Chapter 1. What are 3D cameras? Chapter 2. The LIPS Edge 3D cameras family. Chapter 3. The LIPS Edge SDK. Chapter 4. The NI Viewer tool. Chapter 5. The Point Cloud Viewer. Chapter 6. Accuracy and precision demonstration for the different LIPS Edge camera line. And lastly, Chapter 7. Environment and light conditions versus which camera to use. To ease the training timing, we've set it into 2 parts. As for Part 1, with an estimation of 45 minutes covering Chapter 1, what are 3D cameras with? What is 3D sensing and different technologies? What 3D cameras can do compared with 2D that cannot and applications with 3D cameras. Chapter 2, LIPS Edge 3D cameras family. LIPS Edge 3D cameras overall comparison. LIPS Edge 3D cameras main parts introduction. LIPS Edge AE and S series, LIPS Edge M3 and DL series, and the LIPS Edge L series. Chapter 3, LIPS Edge SDK covering architecture introduction. The location of the LIPS Edge SDK, where it can be downloaded for the installation. NI Viewer for depth, Point Cloud Viewer, other tools location, and a table for a simple description. As for Part 2, with an estimation of 65 minutes covering Chapter 4, the introduction of the NI Viewer, presenting hotkeys, pointer mode, display mode, image registration, ROI, streaming on and off, camera registration, display on and off, recording, streaming and playing it back. Chapter 5, Point Cloud Viewer, resolution change, how to view Point Cloud. Chapter 6, and showing the accuracy and precision within the different LIPS Edge series for the LIPS Edge AE and S series, LIPS Edge DL and M3 series, LIPS Edge L series, and Chapter 7, the environment and light conditions that could affect which camera to use. So let's get started with our Part 1. And within our topic, what are 3D cameras? 3D cameras are devices designed to capture images and videos in 3 dimensions, creating a perception of depth similar to human vision. They use various technologies to achieve this, enabling a range of applications in entertainment, industrial uses, and scientific research. Here are some key features and types of 3D cameras. Key features: depth perception. 3D cameras can capture depth information, allowing them to create realistic 3-dimensional representations of scenes. Multiple lenses. Many 3D cameras use 2 or more lenses to mimic human binocular vision, capturing images from slightly different angles. Real-time processing. Some 3D cameras can process depth information in real time, making them suitable for interactive applications like gaming and augmented reality. Types of 3D cameras. Stereo cameras. These have 2 lenses that capture images simultaneously, allowing for depth calculation through binocular disparity. Time-of-flight cameras. These emit infrared light pulses and measure the time it takes for the light to return, creating depth maps based on the time-of-flight principle. Structured light cameras. These project a known pattern of light onto a scene and analyze the deformation of the pattern to determine depth. "3D cameras offer several capabilities that 2D cameras cannot, primarily due to their ability to capture depth information. Here are some key differences. 3D representation. 3D cameras can create a 3-dimensional representation of a scene, allowing for a more immersive experience. This is essential for applications like virtual reality and augmented reality, where depth is crucial. Accurate depth measurements. 3D cameras can measure distances between objects and the camera, enabling precise spatial analysis. Better spatial understanding. With depth information, 3D cameras can more accurately identify and differentiate between objects, even if they overlap or are occluded in the view. 3D scanning. 3D cameras can create detailed 3D models of objects and environments, which is useful for industries like design, gaming, and architecture. This level of detail is not possible with 2D images. Improved tracking. In applications like gesture recognition or motion capture, 3D cameras can track movements more accurately, providing more natural interaction in virtual environments. Obstacle detection. In robotics and autonomous vehicles, 3D cameras can help detect and navigate around obstacles by providing a complete view of the environment. Realistic simulations. 3D cameras can enhance simulations and visualizations in fields like medical imaging, allowing for better analysis of anatomical structures. Gesture control. 3D cameras enable gesture-based controls and devices, allowing for more intuitive user interfaces compared to traditional 2D touchscreens. In summary, 3D cameras provide depth information and spatial context that are not possible with 2D cameras, enabling a range of applications that require a three-dimensional understanding of the environment. Applications with 3D cameras include industrial and factory automation such as autonomous mobile robots, volume dimensioning, pallet dimensioning, vehicle dimensioning, automated optical inspection, robotics for pick and place, virtual fence, surface processing, smart retail for customer tracking and behavior analysis, service robots, face recognition and liveness detection, touchless kiosk, and volume dimensioning. LIPS provides a complete set of 3D cameras made with the available technology. The LIPS Edge 3D cameras cover the three 3D technologies available, including the time-of-flight series for DL and M3 series, targeted for short and middle-range distances, used for people counting, motion gesture detection. The AE series and S series for industrial use, which are robust and certified against dust and water, come with distinctive characteristics suitable for autonomous mobile robots and factory automation and robotics arms. And the L series, which is suitable for close-distance scanning applications. All of LIPS Edge 3D camera series can achieve an accuracy of 2% or less. Additionally, the LIPS Edge AE and S series interfaces are Power over Ethernet, which simplifies the installation with just a single Ethernet cable. LIPS Edge AE 430 and AE 470 also have edge computing enabled on device that can run at 5 TOPS. And the S series comes with a built-in Ambarella CV2 SoC, which can provide running on edge powerful image processing applications. Let's have an overview for the LIPS Edge AE series. The LIPS Edge AE series active stereo have common characteristics in which the LIPS Edge AE 400 and AE 450 have a robust housing cases with Ethernet port from using a full 8-wired Ethernet cable for power over Ethernet data and power transmission, indicated on the bullet 4 on the top of this presentation. But if in case the installation working environment doesn't have a PO-powered switch, users can also use the power pin from the bullet 5 and supply power directly. For the LIPS Edge AE 430 and AE 470, the cameras are smaller and come with a compact size. The cabling for the power over Ethernet can be purchased directly from LIPS, as the tailored cable comes as fully lockable. For the LIPS Edge DL series, they offer a more compact and small form factor, tend to use for general purposes application coming with an USB 3.0 port. The DL has depth sensor and a RGB sensor for displaying 2D, and for use cases such as people counting, body pose and volume inspection. While the M3 series, being a time-of-flight camera for short distances, based on an interface of USB 2.0, the application can be made for motion and gesture detection. And the L series, using the structured light technology, it comes with its optical components that enable short distances scanning use including face and object scanning, including near-infrared components read as NIR for sensor and illuminator. It also has an RGB sensor for 2D color image output, and the connectivity interface uses a micro USB port, for which can be connected directly to computers either with USB 2.0 or 3.0 ports. Okay, let's get started with the Lips Edge SDK and its steps to use its tools and maximize the potential of the Lips Edge product portfolio. The Lips Edge SDK starts from all the 3D cameras provided by Lips. From active stereo from the AE series with power over Ethernet connectivity, time-of-flight cameras with the DL and M3 series, and the L series for the structured light technology with USB connectors. The Lips Edge SDK allows programs to be developed on 64-bit base platforms and ARM 64-bit platforms from the NVIDIA with the Jetson package. And developers can also create applications for Microsoft Windows, Ubuntu, NVIDIA Jetson Linux and by request Android operating systems. Based on OpenNI2, adopting reusability of common code, it also delivers a complete set of tools for viewing depth, point cloud, and lots more with source code and compiled executables. Supporting major programming languages such as C++ and C# and example codes with Python. Through different frameworks, we are supporting Genicom Protocol, which can connect and interface to Zebra's Aurora Vision, MVTech's Halkin's Industrial Framework, and also supporting ROS2 and NVIDIA Isaac for Omniverse. We have also made developments with API wrappers for Flutter and Unity, which allows a rapid development of software for IoT and AR/VRs. Lips also provides middlewares for software development including Lips Metrics for dimensioning use, Lips Sense 3D Body Pose SDK for skeletal tracking, Lips Face for face recognition, and Lips Scan 3D for scanning use with a desktop software or an SDK for scanning software development deployments. Okay, let's start with the installation of the Lips Edge SDK. Lips Edge SDK can be downloaded from the Lips web by clicking on the Lips Edge SDK download. Once in the developer documentation section, select the link to download link for starting the download. In this training, we will be using Windows as the operating system. Developers can use from Windows, Linux, and ARM 64 SDK that can be found from the Lips Edge SDK download section. For each, the manual for the installation can be found in each Lips Edge camera user guide. And getting started with a brief overview of its tools, the main utilities from the Lips Edge SDK are NI Viewer or Depth Viewer for latest releases, and Point Cloud Viewer for viewing point clouds. And there are also additional Lips Viewer tools that are installed with the Lips Edge SDK. As general overview, let's start explaining what is a depth map in 3D vision. A depth map is a grayscale or colored-leveled image that represents the distance of a surfaces of seen objects from a specific viewpoint, typically a camera. In this map, depth color or levels values may correspond to closer objects and darker values represent objects that are farther away. Depth maps are used in various applications including 3D rendering. They help create realistic scenes by providing information about the spatial arrangement of objects. Computer vision. Depth maps assist in understanding the geometry of a scene, enabling tasks like object detection and recognition. Virtual reality. They enhance the immersive experience by simulating depth perception. Image processing. They can be used for effects like depth of field, where only objects within a certain distance are in focus. Overall, depth maps are crucial for translating 2D images into a 3D understanding of a scene. Our NI Viewer here displayed provides the 3D depth map for the Lips Edge camera series, with rich tools and features. More details will be explained in our Part 2 of the training. A second topic to understand well is the use of 3D is the point cloud. So what is it? A point cloud is a collection of data points in a three-dimensional coordinate system, typically representing the external surface of an object or scene. Each point in the cloud has defined coordinates, x, y, z, and may also include additional information, such as color or intensity. Point clouds are generated through various methods, including 1. 3D scanning. Devices like stereo imaging, time-of-flight, or structured light scanners capture the shape of objects and environments. 2. Depth sensors. Cameras with depth sensing capabilities create point clouds by measuring distance to surfaces. Applications of point clouds include 3D modeling, creating detailed models for design, architecture, or cultural heritage preservation. Robotics, enabling navigation and obstacle detection in autonomous systems. Virtual reality, enhancing immersive experiences by providing detailed environmental data. Geospatial analysis, used in mapping and surveying for terrain modeling and analysis. Point clouds are essential in fields that require detailed spatial representation and analysis. A 3D point cloud can reflect a variety of attributes and information about a physical scene or object, including 1. Geometric shape, the basic structure and contours of objects, showing their size and form in 3 dimensions. 2. Surface texture. When combined with color or intensity data, point clouds can provide insights into the material properties and surface characteristics of objects. 3. Spatial relationships. Point clouds represent the spatial arrangement of multiple objects, revealing their relative positions and distances from one another. 4. Volume and area calculations. They can be used to compute the volume of irregularly shaped objects or the area of surfaces, useful in engineering and construction. 5. Change detection. Comparing point clouds taken at different times can reveal changes in a scene, such as erosion, construction, or other alterations. 6. Object recognition. With machine learning techniques, point clouds can help identify and classify objects within a scene. Overall, 3D point clouds provide rich, multidimensional data that can be analyzed for various applications in fields like robotics, surveying, gaming, and virtual reality.
There are also additional tools from the LIPS Edge SDK package installation, including LIPS Camera Matrix, query-supported video modes, and list camera intrinsic or extrinsic parameters. So what are these? Intrinsic parameters. It includes intrinsic parameters such as focal length, optical center, and skew, which determine how the camera captures images and how it handles lens distortion. Extrinsic parameters. In some cases, it can also incorporate extrinsic parameters that describe the camera's position and orientation in the 3D space, affecting how the scene is viewed. Ni2 center read, which shows depth value at center point of frame. Ni2 point cloud. Visualize point cloud data in 3D. Ni2 raw viewer. Captured and display camera frames in raw format. Ni2 simple viewer. A simplified version to display camera frames. Okay, let's take a break. Hoping that our first part was plentiful for the introduction of LIPS Edge 3D cameras, the characteristics of the technology and its uses, and also to be able to provide an insight of the power from 3D vision. See you back in 10 minutes. So, let's get started with our part 2. As a recap, for part 2, with an estimation of 65 minutes, covering Chapter 4, the introduction of the NI viewer presenting hotkeys, pointer mode, display mode, image registration, ROI, streaming on and off, camera registration display on and off, recording streaming and playing it back. Chapter 5, point cloud viewer, resolution change, how to view point cloud. Chapter 6, and showing the accuracy and precision within the different LIPS Edge series for the LIPS Edge AE and S series. LIPS Edge DL and M3 series, LIPS Edge L series, and Chapter 7, the environment and light conditions that could affect which camera to use. In this section, we'll explain how to use the NI viewer or depth viewer later called in further releases from the LIPS Edge SDK. Getting started with the NI viewer. The tool provides a variety of features that are very useful for viewing and evaluating scenarios when using the LIPS Edge cameras. To bring the Help menu, press the key to display the help list. Inside you will 6 sections with more detailed features. These 6 sections include 1. The General, which shows and hides this menu. 2. The presets, which uses the numerical keys to display depths with histograms, measurement information, side-by-side comparisons, and different depth modes. 3. The display, which allows to turn on or off the pointer, use a full screen, or reset the infrared information histogram. 4. The device menu, using the alphabetical keys, where allows adjustments for the 3D camera including depth frame synchronization, auto exposure, auto white balance, exposure gain adjustments, and image registration for synchronization the depth with the RGB. 5. The player, which reads single frames. And 6. Capture to record and save the live streaming. Here we bring out a particular topic when using the NI viewer, which facilitates the usages of the Lips Edge 3D cameras. From time to time, we will need to evaluate and do minor adjustments to the Lips Edge cameras when searching the best condition for the capture. Using the alphabetical keyboard, we've listed the most common adjustments that are needed, where allows adjustments for the 3D camera including A. Setting it to auto exposure. Capital E or minor E for increasing or decreasing the exposure. Capital G or minor G for increasing or decreasing the gain. Y, which turns on or off the color frames from the RGB sensor from being synchronized with the depth sensor. I, which turns on or off the image registration between the points of the depth to the exact location to the RGB. The M, where it mirrors the image streaming. The P, which turns on or off the pointer. The pointer is a user interface tool. The semicolon, which enables reading single frames. And the spacebar, which allow to pause and resume the streaming. In the NI viewer, when viewing the streaming, the pointer can be useful to provide the depth information, as you can see it from the side-by-side with depth and RGB. The red pointer from the left from the depth will move along on the same location from the blue pointer from the right at the RGB image. While moving the pointer, the values can be displayed on the fly from the bar located on the bottom from the screen. The label pointer value will be indicating depth value in millimeters, with the second value being the coordinates from the XY, and subsequently indicating the frame number and timestamp. The NI viewer allows different views when viewing through the Lips Edge 3D camera series. The display modes can be switched among the numeric keys from the keyboard. For each key number, it will correspond to a different display mode. We will navigate through each of them in the next slides. When the NI viewer starts, the default view will be the depth with the RGB from using side-by-side display. This default view can be accessed through the number 7 key. For displaying a single view from the display mode with depth only, the key number 1 can be clicked on. Other display modes will include the number 2 and 3. The number 2 would display the depth with psychedelic with different color range from 79 to 80 centimeters approximately, with a single color. The number 3 would display the depth will be in millimeters, and within the range of each color, each gap of millimeter will be displayed using a different brightness. In this example, for a more zoomed closer view, from the gaps between the different range on its own edges, we will inspect the range in which the depth is defined is quite close. So from the left, the depth readout when the pointer is placed at the blue zone compared with the depth pointer placed nearby on the red edge provides a close reading. This proves the reading the output is correct. The NI viewer includes a rainbow depth, which may also be useful to identify just by viewing which object is protruding versus a background. For this display mode, the key number is the number 4. A mode to verify if the depth and the RGB are matching, the key number 8 can be used. In this mode, the depth is placed on top of the color RGB output. And to see through it, the key number 9 can be made into transparency to verify if they are properly transposed. When placing depth and RGB through a single output, some displacement may happen occasionally. Lips Edge offers a self-calibration method with the registration feature. As it can be seen from the image of the left, the depth is displaced from the RGB image. But with the registration on, both RGB and depth can be placed accordingly with matching locations. There is also the possibility to have the rainbow depth display mode to be placed on top of the RGB output. For this mode, the key number is 0. Once turned on, it can be seen the rainbow depth becomes transparent, where it is transposed with the RGB output, and see the matching locations. Another feature is using the mouse to draw a region of interest. The use region of interest benefits the viewer on focusing the location of where the interest of view is placed. To enable or disable depth, the mouse right-click can be used to display a selectable menu, in which we navigate through the menu from device going to streams, and from the menu, either depth or color, we could turn it on or off. It is also possible to change the resolution for the streaming. For this, first stop all streams. You can do this by clicking the right mouse, and then from the same menu going to the video mode to select the desired resolution to output. Once changed the resolution, it can be seen in this example, the results from the units of the pointer value when being read from being 1 mm at 64.8, and when being at micrometer the unit, the result of the depth displays 648.4 micrometer. The NI viewer also provides the feature from recording of the streaming of the Lips Edge camera. For this, you can click right on the mouse, select Capture, Start, and then a folder where the streaming will be recorded to. All recording from the NI viewer will be saved with the extension of .oni, in which to open the files the same NI viewer can be used. To evaluate if the 3D depth is useful, let's provide an example in this case. Being A, the original image, the image B, where it can be seen there are dark areas on the marked areas on the left and right, and also on the ceiling, where dark intermittent noise are present, and the last image C, where the same areas marked have depth layers shown, indicating the improvements, including the left area of the reflecting glass wall, the background from the cubicle from the right, and the ceiling where shows a full layer of depth. Another way to evaluate in 3D camera is to verify whether the camera can provide depth under low light conditions. In this example, even though in the dark, the camera can still identify a person and reflect the depth in the room without light. In this section, we will introduce what is called a point cloud viewer. Before we start, just to refresh a little what point cloud is. A point cloud is a collection of data points defined in a three-dimensional coordinate system. Each point in the cloud has its own set of coordinates, usually x, y, and z, that represent its position in space. Point clouds are commonly used in various fields such as computer vision, 3D modeling. They can be generated by 3D scanning techniques, like using the different technologies implemented in the Lips Edge series. Point clouds are often used for tasks like object recognition, terrain modeling, and creating detailed digital representations of physical objects or environments. The Lips Edge SDK has its own point cloud viewer, which is as well installed from the installation process. In the NI viewer, a choice list of resolution and minimum measured unit can be selected from. When starting the NI viewer, the options from a menu can be seen on the left of the screen. As can be seen from the menu, a series of shortcut keys can also be used, such as the H to show and hide the help screen, the P to start or pause the streaming of the point cloud, the S where we can do shading to the point cloud to smooth the output with mesh. In order to navigate through the point cloud, the mouse can be used from using the mouse left click, which rotates around the center, the mouse right click, which can change the field of view of the mouse, and sliding the mouse wheel for moving forward and back. To verify if the point cloud is optimal for using, a simple way is to check on the output plane. When the noise is high, fluctuations may occur causing instability, such as the example from the right. On the other hand, if the noise is low, it may improve the point cloud condition, providing a flat and stable output, such as the example from the left. In this section, we will talk about accuracy and precision. When measuring 3D depth cameras' quality and performance, establishing a common attribute is best to characterize the measurements to represent its performance, hence the preferred metrics but not limited to are Z-accuracy, usually mentioned as accuracy. Precision. Z-accuracy measures how close the depth values are close to the actual distance, called the ground truth. The Z-accuracy is represented in percentage, percent symbol, meaning its variation on its closeness of a measured value to a true value. Precision refers to the actual distance, referring to the closeness among successive measurements carried out with the same method by the same operator under identical conditions. As it can be seen from the 4 target charts. The first one shows a high accuracy and low precision. The targeted measurements are close to the ground truth, but each distance to the ground truth are not close near enough, becoming the image to have low precision. The second chart, the precision is high as all targeted measurements have a high concentration on the same spot. Nevertheless, they are far from the targeted distance measurement, which would become a very low accuracy. In the third chart, the measurements reflected both reading from the accuracy results are dissimilar in many ways and far from being concentrated, reflecting a poor accuracy and precision. And the fourth chart, where the readings from both accuracy and precision are concentrated in the ground truth, reflect a high accuracy and high precision. In these 2 videos, you will see an example why accuracy is important. With the video from the left, you can see the point cloud is stable, while the point cloud from the right is flashing intermittently. The flashes that occur in the point cloud are caused by noise, which can disturb the readings from the accuracy and precision. We have included real actual measurement examples, such as this one with the Lips Edge 430, where the camera is targeted to the orange, 86 centimeters. And measured with a ruler, it shows the ruler measures 86 centimeters as well. On the right, a screenshot of the point cloud with RGB transposed, in which we will show next the original video. As to this video, we've captured the depth reading from the previous scenario to show the reading of the depth distance to a readout of depth of 86 centimeters, reflecting a high accuracy and precision, as well on how the depth levels are displayed to reflect the different Z height from the camera focus. In this video capture, you will see point cloud is zoomed into a closer distance, how the points match precise and accurate locations versus the original RGB image. We have more examples using our Lips Edge DL, using the time-of-flight technology, using the same scene, and measured with a ruler. It shows the ruler measures with 68.5 centimeters. On the right, a screenshot of the point cloud with RGB transposed, in which we will show next the original video. As well to this video, we've captured the depth reading from the previous scenario to show the reading of the depth distance, where the camera is targeted to the orange, providing a reading of depth of 67.3 centimeters, with accuracy of only 1.8% variation, as well on how the depth levels are displayed to reflect the different Z height from the camera focus. As well in this video capture, you will see point cloud is zoomed into a closer distance, how the points match precise and accurate locations versus the original RGB image. And lastly, with our Lips Edge L series, where the camera is targeted to the orange and measured with a ruler, it shows the ruler measures 68.3 centimeters. On the right, a screenshot of the point cloud with RGB transposed, in which we will show next the original video. As well to this video, We've captured the depth reading from the previous scenario to show the reading of the depth distance, where the camera is targeted to the orange, providing a reading of depth of 68 centimeters, with accuracy of only 0.5% variation. As well on how the depth levels are displayed to reflect the different Z height from the camera focus. As well in this video capture, you will see point cloud is zoomed into a closer distance, how the points match precise and accurate locations versus the original RGB image. Lastly, to wrap up this training, we will expand how the environment and light conditions may affect on how to use the different 3D technologies. For considering when using different technologies based on 3D, there are active stereo, where the distance range is better for middle to long range, within an ideal range at 4 meters. As for object type, most objects are acceptable, and the environment, low and bright conditions are acceptable, outdoor and indoor. Noise will increase when distance is increased. Regarding time of flight, the distance range is short to middle range, within an ideal range at 2 meters. For object type, most objects are acceptable, reflective objects may cause some noise. And the environment, preferably indoors, outdoors. Noise will increase when distance is increased. And lastly, for structured light, the distance range, short range, a maximum range of 1.2 meters and a minimum distance of 40 centimeters. For object type, non-reflective types. And the environment, indoors, outdoors must not be directed to sunlight. Noise will increase and depth may not be accurate when distance is outside the allowed range. As you will realize, each technology has its particularities and are suitable for different environment. Understanding the environment conditions is one of the considerations when adopting different technologies with 3D vision. Thank you for attending this training. Hoping this training has been helpful, and contact us for more.